Hi guys, so welcome to the second part of Sarah's day lecture. So in the first part, we talked about BMOS transistors and their structures, their analysis. And now we're going to talk about, mainly about the applications of either NMOS or BMOS transistors. So to know better idea about how can we use this device, we should put it in a circuit and derive some equation or relation that relates V output to V input of the circuit. So that based on that shape, which is like transfer characteristics as we agreed before, we're gonna know what kind of applications we can use this transistor at. Okay, so in the beginning we're gonna study the transfer characteristics of our MOSFET. Okay, so here we have a circuit in which we have RD, we have VDD, and we have a variable VGS. So VGS here is variable; it's not constant. Okay, and we're gonna change this. We will assume that this VGS is changing from minus infinity to infinity, and in each change we're gonna see how much will be the output. Okay, this is basically the idea of transfer characteristics, either in BJT transistor or MOSFET transistor, whatever it is. Good. So this is what we're gonna do. We're gonna change VGS from minus infinity to infinity, and we're gonna check VO, which is VDS, for all these ranges. Okay, what we're gonna see is something like this. This is minus infinity, this is infinity. We'll assume this whole range into three pieces. So the first piece start, end this at that point, which we'll call VGS on, and the last portion or the third portion will start at what is called VGS set. So basically, between these two transition points, we will have these two transition points will divide, the operation of transistor into three regions. The first one is cutoff, in which VGS is less than VGS on. Then between VGS on and VGS set, we have another region of operation, which is the saturation region. So here VGS is larger than VGS on and less than VGS set. And for VGS larger than VGS set, we will work in linear. Okay, good. So why I call the first point VGS on? Because this is the point at which the transistor will turn on. I mean, before this point, when VGS is less than VGS on, we have current equal to 0. Okay, so for the first range in which VGS is less than V threshold, basically the transistor is off. And of course, VGS on is actually V threshold, because we know when VGS equal to V threshold, there will be a channel between the drain and the source, and a current can flow in that channel. So before V threshold, no channel, transistor is off, so the current is off. I is equal to 0, ID. So when we apply this here, we will find that VDS, which is VO, equal to VDD minus ID, RD. ID is 0, so this is basically VDD. So whenever the transistor is off, the output of that circuit will be VDD. Good. So the first point, let's make it, you know, that's fine. So the second point now, VGS set. This is the point, you know, at which the transistor will go from saturation to linear if VGS is increasing, or if VGS is decreasing, it will transition from linear to saturation. Okay, so this is the edge of saturation or linear. An edge is something in between. So at that point, VDS equal to VDS set, which is VGS minus V threshold. So let's determine it. So in the lab yesterday, we just write an equation, but we don't know from where this equation came. We will see now. So since we still at saturation, because we are at the edge of saturation, so we still belong to saturation, ID, and remember, since we changing VGS, you know, there is, you know, AC and DC part in general. So I mix, you know, small letters for the symbols and capital letters for the subscripts to say that, okay, we have AC and DC, or AC superimposed on some DC. So ID will equal to half Kn VGS minus V threshold square. Remember, we want now to calculate or find an equation for VGS to calculate this guy. Okay. We know also from the circuit that VDS is equal to VDD minus ID RD. And VDS in that point equal to VDS set, which is equal to VGS minus V threshold. And particularly at that, you know, at the edge now, we want to determine the VGS value that makes the transistor at that edge point. So this is VGS set, basically. Good. So VDD, which is VGS set minus V threshold, equal to VDD minus ID, which is half Kn VGS set minus V threshold square RD. So this equation is only has only one unknown, which is VGS set, the point of the input at which we will be on the edge of saturation. We consider all other values are known, like VDD, V threshold, Kn, RD. Okay? So based on that, we can simplify this into the following equation, in which we have minus half Kn RD VGS set square plus VGS set times Kn RD V threshold minus 1 plus V threshold plus VDD minus half Kn RD V threshold square. This is equal to 0. And of course, don't, you know, try to memorize this equation, you know. Usually when we're gonna use it, we will have VDD will be known, RD will be known, okay, and Kn will be known. So we can just, you know, integrate the numbers and it will be easier, you know, to read and satisfy. So we can take example. So, but basically, this equation, if we know VDD, if we know RD, if we know Kn, if we know V threshold, will give you two possible solutions. But you will find that one of them is less than V threshold, which is wrong. And the other solution, let's write it solution 1 and solution 2. And solution 2 will be larger than or equal to V threshold, which is accepted, of course. Or larger than V threshold, not even equal, larger than V threshold. Because we are away from the switching point from off to on. Okay? And we take an example, for example, in the lab yesterday, where VDD was 15, RD was, I think, 1 kilo ohms, Kn around to 100 milli, you know, and this gave us, you know, I think 2.53, yeah. And the other value was just less than V threshold, so we didn't consider it. Okay, so this is how to determine VGS set. You know, if we assume that the input is increasing until some point, we're gonna move from saturation to linear, and this point, the input at that point is called VGS set. Okay, but how about the relation between VGS or the input and the VDS in that region? Okay, so that will basically give us, you know, the great idea about how we can use transistors. So I will go into conclusions directly. Okay, although we will make the derivation in another slide, but basically what we will get, or the relation between VGS or V input and V output, which is VDS, is something like this. So we have two transition points. We have VGS on, which is V threshold, and we have VGS set, in which you can calculate from this equation, very big equation. So in the beginning, we will have VDD. Then we will have, as we will see later, it's a quadratic relation between VGS or V input and V output. So it will be something like this. It's a little bit curvy, especially at the end. Then the third, so this is, you know, first and second region. Now the third region. It's also a quadratic relation, although most of the time VDS will be very small. So it's decreasing like this, but, you know, almost flat. Although it's decreasing, but very, you know, with a very slow rate. So it's like just like flat, as we will see, as we saw also yesterday in the lab. Okay. So basically, if we name this 1 and 2, here is cutoff, here is linear, and number 3 here is the saturation region. So in regions 1 and 2, we can use the transistor as inverter. So basically it has two applications. Number 1, as inverter in digital circuits. And why? Because V input is low, and low means less than V threshold. the output of VDS will be high, VDD. And when the input, much larger than, or, VGS set, we will have low output. So it's inverting. If you have input high, you will have output low. If you have input low, you will have output high. And in region 3, we can use a transistor as amplifier. As we will see in the next slide, we can even have a linear relation if at certain conditions for the input, and we will see that there is a gain, really. There is amplification. So let's see that. So for the same circuit, okay, let's do a derivation here. So again, we have the same circuits. We have VDD, then we have RD, and we have our NMOS here. Here is VO, which is VDS. And we have two sources, VGS and the voltage that we want to amplify. Both of them is VGS. So, yeah. So you can say the DC portion of VGS and the AC portion of VGS. Okay, so the input here is V small GS capital, where VGS is equal to V input plus VGS capital. This is pure DC for the Q point, and this is pure AC, the signal to amplify, the signal to be amplified. So two observations here. Number one, since we want to use the transistor as amplifier, then we are working in saturation region. So to amplify, we must work at the saturation region. Number two, most of the time, since we want to amplify something, this something should be small, right? So we have many cases in which the input is really very small. So in many cases, the input is very small. And that's why it's important to study the characteristics of the circuits if we assume that the input is really very small. And very small means, as we will see later now, maybe in 5 minutes, much less than VGS minus V threshold. So very small means that V input is much less than V input maximum. So it's generally a variable, signal that has maximum and minimum. It's AC. Small means VI maximum is much less than VGS minus V threshold. Okay. So let's see how the circuit will behave under that condition if it's really small, very small. Okay, good. So VO or VDS, V small, DS capital, because now the voltage at the drain source has part of it is DC and part of AC is AC, is equal to VDD minus I small d capital, again because the current now is changing because the input is varying, the VGS is varying, and the ID is small capital, small letter capital subscript, because again there are two signals, AC or two components, one AC and one DC, multiplied by RD or times RD. Okay. And remember, we are in saturation. So ID is basically Kn over 2. Then V input, which is now two stuff, Vi plus VGS minus V threshold square. Usually we call that voltage VGS minus V3, we call it overdrive voltage. So this is called overdrive voltage. V overdrive. But don't worry about the namings, you know. I will just remove this VGS minus V threshold and call it so, just to make our, you know, symbols less, because it's messy now. Okay, so VDS equal to VDD minus RD Kn over 2. And here, this guy is overdrive, so V input plus V overdrive. I'm sorry, overdrive is DC, complete DC. So V overdrive. So everything should be capitalized. Equal to VDD minus RD Kn over 2. And now we're gonna, you know, make this squaring. So Vi square plus V overdrive square plus 2 over V overdrive VO V overdrive. Good. Now, based on the assumptions that V input is much less than VGS minus V threshold, that means that Vi square is much less than VGS minus V threshold, which is the overdrive square. And let's give an example. 2 is less than 20. You know, the ratio between them is 1 to 10. Let's now square both sides. So 2 will be 4 and 20 will be 400. Now what is the ratio? The ratio is 1 to 100. Okay, so if something is less than something, then the squaring of that stuff will be much less than the other stuff. Okay, so basically, if we assume again that the input is very small, so we can ignore Vi square plus V over. So this is basically means that Vi square plus V overdrive square is approximately equal to V overdrive square. And we can just neglect Vi square. So let's rewrite now VDS after that assumption. So VDS equal to VDD minus RD Kn over 2. And this will be V overdrive square plus 2 V overdrive, VO V overdrive equal to VDD minus Kn RD over 2 V overdrive square plus, and now I will bring it back to its original shape, VGS minus V threshold square. I just removed V overdrive and, you know, go back to its original equation, original symbol or term, plus or minus, because Kn will just, you know, so RD Kn over 2, and the 2 will go with 2, so we don't need this. V overdrive and VO V, and again V overdrive can be go back to VGS minus V threshold. And now we will have a minute here. So VDS. Let's write this as follows. So VDS, okay, let's write VDS equal to VDD minus KNRD over 2 VGS minus V threshold. So what is Kn over 2 multiplied by VGS minus V threshold? This is basically if there is no AC input and we only have DC, okay, this will be ID capital. So this is VDD minus RD ID capital. And ID, you know, is the DC portion of ID small, I small d. Remember, we have two components, AC and DC. Minus RD Kn VGS minus V threshold, which is all constant, multiplied by VO. Okay, what is this? This term. This term is basically the DC portion of VDS. So this is VDC. I'm sorry, VDS, V capital, DS capital. So if you don't have AC voltage, the voltage here will be VDD minus ID capital multiplied by RD, and ID is just DC. Okay, minus constant. I will call it GM for some reason now. I'm sorry, constant. Yeah, so constant is RD, which is dependent on the circuit, and another constant here, which I will call GM, and you will see why I call it GM. VO. Good. Remember this voltage VDS, V small VDS capital, is the AC and DC portion at VDS. So this is equal to, let's call it VO, which is the AC portion, and VD is the DC portion is just VDS. So this go with this. So VO equal to, I'm sorry, this is V input, not this is V input. I am very sorry. V input. Yeah. V input. I just confused this. Okay. VO is equal to, so DC is equal to DC. So the AC will be equal to the AC. So GM RD VI. Now, if GM RD is larger than 1, we will have amplification. So we can design our circuit such that the multiplication of Kn VGS minus V threshold by RD is larger than 1. So we will have amplification. So this is number 1. Number 2, VO is out of phase with V input. Again, just like BGT. So BGT amplifier, they were out of phase, and here also they are out of phase. Okay. And as we will see, in the next lecture, this is actually the amplification. So this is EV, the amplification. Or to be more specific, this is EV node. The amplification, assuming that we are not connecting a load, RL. Okay. And now this mysterious term, GM, which is equal to Kn VGS minus V threshold. This is just like GM of the BGT, although of course it has a different equation to be evaluated based on. But it's again the transconductance. So this is the transconductance. So remember, VGM in BGT transistor was VT over IB, or VT, I'm sorry, ICO, I'm sorry, IC over VT. So here is also our GM. Okay. That's very good. Another and very important observation is that we know that when we have input, and this input is part AC and part DC, we will have output that is also part AC and part DC. Okay, so basically that's what we get, part DC and the part AC. And we know for sure that the DC part come only from the DC part, the DC input, the battery, VGS, V capital, VGS, C capital. Okay. So basically, another assumption that we can do in this analysis is that we can, again, like VGT, solve the AC domain by itself, canceling all DC sources, and solving the DC domain by itself, canceling all AC sources. So the AC and DC domain are decoupled, you know. So DC analysis, we will have DC analysis to determine the Q point, in which we cancel all AC sources. And we will have AC analysis, in which we cancel all DC sources. And actually, this mysterious, you know, transconductance can be derived in another way. So we knew that from BGT that GM is actually, you know, is partial I output over I input. So it was partial IC over or derivative of IC with respect to VBE. Here, it's also partial ID with respect to something in the input, which is VGE, or I'm sorry, VGS. Can we do that? Yeah, we can do it. So we know that, so partial or partial VGS. And what is ID? It is Kn over 2 VGS minus V threshold square. What is the derivative of that? We go, 2 will go in the, we multiply by Kn 2. So it will be Kn VGS minus V threshold. So another, this is another derivation for it. Okay. We derived it basically first from the circuit analysis, then by the formal definition. And of course, both they should merge into the same stuff. Okay. GM usually has multiple forms, and of course, all of them are equivalent. So GM till this moment is equal to Kn VGS minus V threshold. It can be written as with many, you know, they can all lead to each other. Yeah, 2ID over VGS minus V threshold. Okay, and also can be equal to the square root of ID 2ID Kn. If you remove ID here and put Kn over 2 VGS minus V threshold square, you will get, you know, the same equation, the first equation. Again, if you remove here this ID and also put Kn over 2, you know, you will again go back to the first equation, this equation here. Okay, so they all lead to each other, you know, but you may find this definition somewhere and this another definition somewhere, so you can just, you know, combine them, or you should know that both are the same, or all are the same. Okay, so the bottom line here is that we can use the transistor to amplify signals. Okay, and we see that there is amplification called the GM-RD, and it's based on this, it's dependent on the circuit parameter like RD and our transistor characteristics and the biasing that we get. So all these parameters can lead, if you choose them right, you can have GM-RD larger than 1, so you can have amplification. For small signals, we can decouple the AC from DC. I mean, we can do the DC analysis by itself, canceling all the AC sources. Then we can do the DC analysis by itself, canceling all the DC sources. Okay. This is number 2. We also get the transconductance parameter. Okay, and it has many forms as we see here. Okay, and of course, all of them just lead to the same stuff. Okay, so next time I'm gonna use these observations and these notes and start to, you know, analyze NMOS or BMOS amplifier circuits. Thank you very much, and have a great day. Bye bye.